So I'm giving you the conclusion of my talk in the title, and so I want to get there. All right, and I'm going to start with exactly what Dan said that you're not interested in, which is beautiful picture. I don't have the nice movies that Dan has, right? I'm just a mathematician, so this is the best I can do, and nonlinear dynamics produces wonderful pictures of chaotic attractors and things like that. It also produces, and I think this is extremely important, very, very complicated bifurcation diagrams. And to me, the reason I'm starting with this is that we're kind of stuck with this, if we do nonlinear dynamics, is this wealth of complexity. And my take on it is that it's beautiful mathematics, but then if you want to do something with it, it's crippling, because there is just so much structure out there. And somehow what we need to do is to isolate what's the structure that we care about and figure out a way to ignore the rest. Since Conley's name has come up, I thought that maybe this is a good place to start. So this is the pictures that I showed you. In some sense, the theory was already well known by the early 70s. When Conley published his monograph on his vision of dynamics, which was a topological approach to nonlinear dynamics. And that's easy to say now, but I think what's easy to forget is that when we talk about qualitative dynamics and start with Poincaré, but kind of instilled in the mathematical community by Smale, this really was a theory of differential topology. And it's an analysis theory. And what Conley did was to say, well, let's try to look at this subject just with the topology rather than with the differential topology. And what he and his collaborators, students showed was that with this approach, you could produce a description of dynamics that was robust with respect to perturbations and parameters. And that, in some sense, gets rid of bifurcation diagrams. In some sense, I mean, this is very delicate. Bifurcations are fundamentally important, but at the same time, bifurcation diagrams for arbitrary systems are just way too complicated. We know we can't hope to resolve them. So in Conley's language, and this is kind of the part of the thesis of what I'm talking about, is that he says that if in my language you can understand the dynamics of this differential equation at a particular parameter value, then if you're sufficiently close to that parameter value, then in the language that he's developed, you still understand the dynamics. So this language of Conley really has two parts to it. One is the decomposition part, and Dan has actually hinted at that quite a bit. And the other is a reconstruction part. So let's start with the decomposition part. And I'm not going to go into any details. I'm leaving all the details for Bill Calise and Marcio. They're senior people. They've worked on this for a long time. And then the really interesting stuff, where this stuff is still falling apart and we can't make it work, that's poor Everton, the postdoc's job to present that, right? So, I get to show you the big picture. Everything looks cool. Bill and Marcio have to show you how things actually work. And Everton, of course, has to show the failures and the struggles. That's the hierarchy of academia. So Conley introduced this notion of a Morse decomposition, which is a finite collection of compact invariant sets that are ordered by the gradient-like flow. But the real thing you should be taking out of this, and this oftentimes gets lost, is not the invariant sets themselves. They can be very complicated. They can be very simple. It's the order structure. That's what's really important from Conley's decomposition. Now, if you're looking at it something like this, there's a bunch of what looks like unstable stuff. You come in here, maybe this is a periodic orbit, but you're likely to leave it and end up down here. So the stuff that's observable is going to be at the bottom of the Morse decomposition. And that's the notion of an attractor. But let's think about attractors a little bit more generally, and that is just some invariant object where if you have a neighborhood of it, you move inward on that neighborhood and you end up on that invariant set. And what Conley showed, and this is absolutely fundamental, and I think Bill will spend a lot of time talking about this, is that these are actually equivalent ideas, all right? So understanding Morse decompositions, which actually are computationally very easy to access, is the same as understanding the collection of attractors. Okay, so that's the decomposition part. And then the reconstruction part is something called the Conley index. So this is an algebraic topological device. And I'm going to black box it for most of this talk. But the fundamental thing is that if somehow you go off and you compute a non-trivial Conley index, then there must be an invariant set. And there's kind of two pieces that you need to compute this Conley index, two sets. And what this Conley index is doing is telling you something about the structure that has been localized by these two sets. And as soon as you kind of say it that way, then you worry about, well, how much does it matter what these sets are? And the fact is that if these two sets, they have to solve some they have to satisfy some properties, but as long as they give the same invariant set, then the Conley indices are equivalent. So this really is an index in some sense of invariant sets up to, well, deformations, because we know that bifurcations take place. They can lead to very complicated stuff, but I've already told you the Conley index is robust with respect to perturbations. So it has to be an index of a type of invariant set rather than an invariant set itself. Okay, so I think I'm being fair to say that these are the fundamental contributions of Conley. Obviously, he did a lot with this, but you know, if you noticed, he passed away in 1984, and then you could ask, well, what's happened since then? All right. So, and the details of this, I think Bill and Marcia will spend a lot of time talking about. So I'm just going to again gloss over it. On the decomposition side, you know, we consider a dynamical system, think of it as a differential equation or a map. And what we've learned is that if you give me a decomposition of your phase space, and by decomposition, think of triangulation, you know, cubes, polyhedra, if you're going to be fancy, regular CW complexes, and some kind of understanding. So let's just say analytic bounds on the approximation scheme that you're going to use to understand this, then Morse decompositions can be extremely efficiently computed. Now, I put the efficiency in bold because that's what we can do. The approximation and the decomposition are in italics because this is really where the rubber meets the road at this point. And just like numerical analysis is constantly evolving because people come up with new ideas of approximation, that's the way you should think about this. There's still lots of room for improvement on how you want to do approximations and how you want to do decompositions. But we have lots of results where we decompose a space and we compute and we get Morse decompositions. The second, and this is more theoretical, but equally important, is that any Morse decomposition can be computed given a fine enough decomposition. All right, so, okay, you need a lot of computer power, but this really says that the Conley decomposition part is a computable theory. It's not an abstract mathematical existence theory. Everything in there can be computed. The same thing, so the Morse decompositions are rigorously computable, and the same tools that we use to get these computations up here allow us to come back and that you know, there exists a sufficiently small neighborhood. We can actually give statements, here's a mu, and over this mu, any parameter value that's within the system you've computed at is going to have the same Morse decomposition. So we can not only compute at a single parameter value, we can compute on neighborhoods of parameter values and know the size of those neighborhoods. So we can kind of cover the space of dynamical systems with these kind of computations. On the reconstruction side, this is this Conley index idea. And there are a bunch of theorems that have been proven that kind of say the basic building blocks of what you care about in dynamical systems, they can be retrieved from algebraic topological statements. You know, you compute this Conley index, whatever it is, it's a homological computation. You typically need to know something a little bit more, but the result is that you get things like chaotic dynamics or periodic orbits or connecting orbits or Lyapunov functions. I mean, these are things that are computable. So the moral is that, you know, algebraic topology in the form of homology, and I emphasize homology because homology is computable, and I think Marcio will talk about the code that we've developed to compute homology. It's sufficiently powerful for allow us to obtain many of the qualitative results that we care about, all right? And we only need combinatorial information to do this. So 3 points of great practical importance are that the decompositions, such as triangulations, you know, kinds of things that people normally use to break up space can be used to compute homology. Homology is easier to compute than one might believe. And this, I find very amusing that I'm writing this at this point in time, because Bill and I started thinking about this in the early 90s. And at that point in time, I was kind of like, well, I learned how to compute homology in grad school. I know there's an algorithm. And so, well, Bill and a grad student wrote a program to do it, and we gave it a simple problem, and it ran and it ran and it ran and it ran and it ran. And that's when I realized that, you know, actually computing things was a serious subject, and that homology might be something that's hard to compute. But since then, we've come up with algorithms that are surprisingly efficient. So at this point, we are computing homology in high dimensional complexes, 10-dimensional complexes. I had a grad student who computed homology on a 29-dimensional complex, where that complex started with over 6,000 29-dimensional cells. I mean, that just should not be able to be done. But it says that this is the kind of thing, there's a lot of work to be done in this subject, but there really is hope to compute things that I did not think would be computable. And the same computations that lead to Morse decompositions are also the computations that provide you with the cellular input to compute the Conley indices. So we're not having to do something different up here from down here. And I think that again leads to this idea that we can efficiently compute decompositions and compute, reconstruct the dynamics in one blow. All right, so I think we've made a lot of progress over the last 20 or 30 years on these kind of points. And so I kind of want to finish with what's next, all right? And so my perspective is that, you know, I kind of started with classical dynamics, which is differential topology. It involves analysis, it involves bifurcation. If you get results here, for example, by numerics, you get very, very high precision results, potentially. But what Conley did was he said, let's strip the analysis out. And from Conley, we realized that we can now think about this as a combinatorial subject, the post-set structure of Morse sets, of Morse decompositions. We can do the reconstructions, again, with a combinatorial theory, homology. We get rid of the needing to understand the details of bifurcations. We have a sheaf theoretic structure that allows us to interpret what Conley's telling us about. And because it's so robust, we can actually hope for accurate statements about the dynamics. We can tell you what's true. The accuracy might not have much precision to it, but there are ways to guarantee that what has been said is correct. All right, so, you know, there's been a lot of interest in, you know, uncertainty quantification. This is kind of a statement that you can certify, you can give certifications of certainty, but you might have to give up something on the accuracy, all right? So going back and forth is, I think, it's a very interesting subject, and I think we've made a lot of progress in that. And Bill and Marcio will talk about that, right? How do you actually do the combinatorics? We know a lot more about kind of the homology theorems that tell us about the dynamics that we're interested in, all right? So this path from left to right, that's what Conley did. And I think over the last 30 years, we've made a lot of, Tammy, if you could mute. We've made a lot of progress towards understanding classical dynamics. Where I think we're at now is in this era of data-driven dynamics, and this is why the title of my talk, and I think Dan already hinted at this, right? They don't have, you can't know enough about your system to control everything. So I think we're now in an era where we want to solve complicated problems, but we're limited. We have sparse finite data. If you give me enough data, then I claim we're back up here in this domain and we know what to do. But in this sparse finite data of complex problems, we need to build surrogate models. And there are different kinds of surrogate models that can be built. And Everton will talk about that in his talk. You can think about surrogate models, and this is kind of where Everton's at, of going exactly from the time series data that you're seeing and trying to fill in with some kind of analytic representation what should go there, or maybe analytic in the sense the computer has stored a bunch of information to try to fill in the missing data. Or another approach that is this idea of network science. In my case, because I'm interested in dynamics, these edges not only represent relations, but they typically are meant to represent causality. This has an arrow to this because somehow what this does influences what that does. Again, I think of that as a surrogate model. It's probably not enough to get dynamics. You have to impose yet a little bit more structure. But this is where we're at right now in trying to use these combinatorial topological methods to understand dynamics. So I think at the moment, I don't want to downplay how much work there is here. It's really interesting. You will hear some of this, but this attempt to try to go from these very sparse amounts of data that we're learning into, well, I like the classical representations. I was taught about differential equations. I understand models when somebody writes down a differential equation. But maybe the fastest way to get here to understanding is actually going to go through this combinatorial type models. So that's maybe what this work, from my perspective, what I'm hoping to see in this workshop. And so I will stop with that if there are any questions. Oh, Linda.
So does the Conley index actually allow you to reconstruct the order? Seems like you had the pieces for the dynamical system, but then you needed to reconstruct the order, or does this not?
So the order is, we compute the order from the pure combinatorics. Well, okay. So we compute a potential order from the Conley index, from the combinatorics. But then you could ask, is it really possible to go from this invariant set to that invariant set? I mean, the partial order might say, yeah, this is lying below that, but whether there's actually a connecting orbit or not, that's the place where the algebraic topology comes in.
Okay, thanks.
I actually guarantee that. Dan.
Konstantin, yeah, if I could ask, I wonder how interested you are in the hybrid world. So there are lots and lots of ways in which one imagines that hyperbolicity could be re-imported into the hybrid world, and that's a different discussion. But it also seems clear to us, particularly when we take the Conley lens, that the hybrid systems are likely to introduce new bifurcations. And so some of us are starting to puzzle over how to compute the Conley index in the hybrid setting, exactly because we want to trap these topological bifurcations, whatever that means. I wonder if you're sympathetic to this, or if this is interesting to you, or you think there's hope here.
Maybe I'm being too naive, right? Because I haven't studied it enough. I think if it's, okay, so Conley was my advisor. And one of the things that I heard him say very often was, if you can observe something, then there should be a way to represent it topologically, right? we're really just working with posets and cellular complexes here. I would be shocked if this kind of language over here couldn't handle what you're doing. So yes, it's interesting to try to do it. If you can show me that it can't be done this way, then it becomes super interesting because it goes against everything I believe, right? That is, if you don't have a sense of continuity, and that's topology, then there's no way to do any sense of prediction, right? Or guarantee of what's going on. So
I mean, is there hope that the RIPs in the Conley index might themselves have structure that's combinatorial but more primitive than the nice algebra, the nice quasi-linear algebra of homology?
let's talk. I need to see some examples there.
Yeah, we don't have them yet. Okay, great.
Okay. Yeah, I need to see examples before I. Yeah. We got time for one quick question, if there is one.
Konstantin, is there any information about the type of networks that you get?
Oh, I don't think of the networks that we get. I think of these networks that I've shown here as what, I mean, I'm mostly interested in kind of systems biology or ecological type networks here. So I think of that as being handed to me by the biologist. And what we've been developing, and I don't think it's going to be talked much about here, but what we've been developing, and this is especially with a group at Montana State with Thomas Gideon, are techniques to be able to, you hand me the network and I'm going to tell you what the dynamics is. So we're really just, you hand me the network, that's the input to our software. It does all this work for you and then tells you something about the classical dynamics. That's what we're working on right now from the network side. So I don't make the networks. I take the network as the given rather than somebody giving me a differential equation. They give me this network. Did that answer the question?
Yeah, thank you.
Okay, why don't we give people a 5-minute break? I think it's Yuli is it Yuli who's next? I have to stop sharing my screen. Is it Yuli or Bill?
I think it's me.
It's Bill. Okay, Bill, do you mind if we start 5 minutes late?
No, that's fine.
Okay, let's start at 1:05. All right.
Okay.